So today I'm going to be talking about performance testing, but in a very specific, performance testing in a very specific way, which I think is quite unusual. I'm not sure if you'll agree with me, but we'll see. I'm going to be looking at performance testing through the lens of experimentation, hypothesis-driven development, if you like, and how performance testing can help us design our software in a slightly different way than we might do normally. I'm not going to be talking about the million types of performance testing that we could do, so soak testing, stress testing, ramp up to high load testing, blah, blah, blah. But it'll become clear over the course of the talk, I hope, what I will be talking about. So first of all, thank you to the organizers for inviting me back. The last time I was here, I don't know if anyone remembers, but I think it was 2011, so very early days, and I did a talk called Java the Unix Way, where I introduced the concept of micro applications. I think it was 2011, might have been 12. And micro applications became microservices. So GeeCON is where the microservice thing started. I don't know if you knew that. That's actually true. That is actually true. So I work for a company called ThoughtWorks. We're a consultancy. There's about, I guess, nearly 5,000 of us worldwide now. We do a whole bunch of stuff, so consulting, advisory. This is where I spend most of my time these days. Still write code, but not as often. And in general, we build bespoke software for our clients. That's kind of what we do. Over time, we've given quite a lot back to the community. We're really passionate, actually, about sharing what we do, sharing better practices, better ways of working. So you might have seen some of these books. They've kind of become canon, or some of these open source projects. So we've got things like Selenium, Pico Container, which is one of the first IoT containers, IOC containers, I.O. containers. Cruise Control, which was the first continuous integration server. Then you've got all the books, more recently building microservices by my former colleague, Sam Newman. Buy them, they're awesome, or something. So a bit about me. As I said, I've been at ThoughtWorks about 10 years. This is probably what I'm best known for in the community, is defining microservices and what microservices are. So Martin and I did this a few years ago now. Wrote a paper about what we were seeing in the world, what we were seeing successful organizations doing, large ones, small ones, our clients and others. And it's been quite successful, turns out. I don't know how many talks at this conference are about microservices, but a fair few of them. But I can claim to be one of, I guess, 3 people who named microservices, and Martin and I certainly defined them. So that's my claim to fame, for which I apologize, because we are now seeing an awful lot of problems being introduced by organizations jumping on the microservices bandwagon. It's become the new enterprise service bus. When IBM sell microservices, you know something's afoot. Anyway, I'm not going to talk about microservices today, other than incidentally. Today I'm going to talk a bit about the scientific method first. So first of all, I'll introduce the scientific method, or rather give us a refresher on what it is, and the approach it can lead you to take when building software. I'm then going to talk through some of the things I think we need as prerequisites to use this technique of hypothesis-driven performance testing. And then I'll talk through an example of where I've put this into practice at scale, and some of the tools and techniques we've used to do it. So first of all, I'm going to ask the room, does anyone know who this is? Feynman was the answer. Yeah, Richard Feynman, Nobel laureate in physics. He's a fanatical bongo player and safecracker, as well as being at Los Alamos working on the bomb project. And Richard Feynman has got a really lovely series of lectures and a book on characteristics of physical law. The characteristics of natural law, it's called. And so I'm going to let the expert on physics and what physics means and what science means, Richard Feynman, explain to us a bit about what the scientific method is, or give us a refresher for those of you who already know. So let me do this.
look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we no, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all.
So I think this is quite a powerful description of what science is, right, at its heart. All right, you have a look at the world, you observe the world, you make a guess about why the world is like it is, right? You compute the results of your guess, and you compare that to nature, you compare it to an experiment. And then, I love this bit at the end where he talks about, it doesn't matter who you are, doesn't matter how beautiful your guess is, if it disagrees with experiment, disagrees with nature, it's simply wrong. And this is at the heart of the scientific method, the heart of science, why it's been so powerful for us. So I'm going to use Richard Feynman's description of this to walk us through what I mean by hypothesis-driven performance testing. So give me 1 moment. We'll do that. We'll do that. So the first thing he says is we observe nature, right? This is the first step. The next thing we do is make a guess. We make a guess about why nature is like that. Then after that, we compute the implications of our guess, and we compare this with nature. We compare it with experiment. And then we draw a conclusion. I'll come back to this in a sec, but first I'm going to talk about how we usually do performance testing, right? How we usually do performance testing on our projects, in my experience certainly, right? So how do we normally do performance testing? Well, my experience, performance testing is one of these things we do at the end, right? It's one of the things we do to prove that we can go into production, and we'll be performing in production. Or if we're in production already, it's one of these things we do as part of a release cycle. Maybe we do like a 2-week performance testing cycle or something. And quite often, you end up, even in agile projects, with this sort of process going on. We'll do some iterations or sprints, whatever you want to call them. In ThoughtWorks, we talk about iterations. So you'll have iteration 1, 2, 3, and then suddenly you'll go into this like hardening phase where we have to work out whether we're still performant, work out whether we're passing regression, and so on. So we have this kind of, it's not even a sandwich, because we don't do performance testing at the start, we just do this performance testing at the end, just before we're about to go live. And I think there's a better way of doing this. And this is also tied in with this kind of process that we often use, where lots and lots of small changes that we make on our projects are all batched up, waiting to be regression tested, performance tested, etc. So we have this long wait to see whether we're actually, whether our software is functional from the perspective of performance. And in many organizations, this takes a long time, right? In many organizations, in order to deploy software, we're talking weeks, if not months. So one organization I'm working with at the moment, even though they're working in the online space, they're a retailer selling stuff, right? Even though they deploy every 2 weeks, right? So that's a deployment every 2 weeks. But it actually takes them 26 weeks, the lead time for changes. If I make a single change to a line of code, it's 26 weeks before it actually gets into production, and there's 3 weeks of performance testing before that. 2 weeks of performance testing. So it's very difficult to go through this loop. Is my laser working? Yes. To go through this process, observation, guessing what's wrong, or guessing what can be made better, computing implications, comparing with nature and drawing a conclusion, if you're not going to find out the results, if you're not going to be able to draw a conclusion until 26 weeks after you made your guess. We're building software, we're not working at CERN, right? We should be able to do this in a much more rapid manner. So, What do I think we actually need in order to run proper experiments using performance tests? So back to our scientific method diagram. So I think the first thing we need to do is we need to have the ability to inspect our current performance quickly and easily, right? We need to be able to observe what our system's doing currently. We then need to make a guess, as Richard Feynman said. We guess that if we do this thing, it'll make performance better. We then need to be able to make a small change. We need the ability to make small changes. We need to be able to measure our results, right? Compare our guess, the results of our guess with experiment or with nature. And then we need to draw a conclusion. Was the guess right? Based on data, not based on who I am or how beautiful my guess was. You know, in software architecture land, we'll talk about caching later, and using a cache. You know, but quite often what we do is, you know, we think really hard and just use our experiences. I've been in the industry for 20 years, therefore, if I put a in-memory cache in, it's going to make things faster. Right. Does the data tell us that that's the case? Right. Can we drive experiments that will prove that's the case or not? So what do we need then in order to do this? Well, I think the first thing we need is good monitoring. And I'll unpack some of these terms because I use them in a very specific way. We also need a brain, right? We need to be able to think in order to create these guesses. We need the ability to deploy rapidly small changes. I would argue we need some form of lightweight performance testing rather than the sort of heavyweight load runnery or Gatling or whatever sort of tests that we normally run. Locust, what's the other one? Bees with machine guns? You come across that? That's a performance testing framework these days. Yes, someone at the back is using that. So those are the things I think we need. Good monitoring, a brain. We need the ability to inspect our system. We need the ability to compare the results with experiment. So what do we mean when we say good monitoring? Because I use this in a very specific way. So I think we need these things, these 5 things actually. Monitoring unpacks into 5 different things. So the first thing is instrumentation, right? We need to be able to have our code that we write describe what it is doing to us, and similarly with hardware and software. Similarly with the hardware and operating system level software that we're using. We then have telemetry, right? Telemetry is the ability for that software to communicate what it's doing to us. So things like StatsD, CollectD, various other sort of frameworks to do that. Then you have level 3, which is the kind of actual monitoring itself, a way of visualizing what's going on in our system. So we need the ability to do that. And then we've got finally the sort of, you know, alerting, the ability to take action in response to an event in our system, maybe good or bad. And then, you know, for extra bonus credits, we've got, you know, predictive alerting, which is, you know, we've got some kind of machine learning thing running, which is going to tell us when a hard drive is going to fail before it fails, or when our microservice is going to die before it actually dies. So for the purposes of this, what I'm going to be talking about is the first 3. And we need instrumentation, telemetry, the ability to get information to us, and the ability to visualize that in some way. So, consider 2 services running on some hardware. And for those of you who know Simon Brown, the guy behind Structureizer and the C4 diagramming model, I draw diagrams like this purely to troll him. So if he watches this video, he normally tweets, you've done it again, James, you've drawn a rubbish diagram. But it's for trolling purposes. So we've got a service running on some hardware, we've got another service running on some hardware, we've got a request and response coming into one service which triggers a request and response to a second service. This is a pretty simple setup. So what do I mean when I talk about monitoring in this sort of circumstance? Well, I would say at a fundamental level we need to know how long each request throughout the entire system takes. So a request comes in, triggers a request off to the other service, and a response and a response. We need to know that sort of round trip time. The services themselves should be communicating or should be registering and communicating how long that takes. I would say we need to know, we need to have circuit breakers between the 2 services. So circuit breaking meaning we know exactly how long it takes to make a request and receive a response, and can take action in the case that it becomes too long, in the case that we have a network partition between these 2 things. So circuit breaking, we need the ability to correlate how long requests take throughout the entire system. We also need the ability to understand what's going on with our hardware. So we need the ability to understand if our OS is performing, what our CPUs are doing, what our disks are doing, and what our memory is doing. And there's a whole ton of tooling out there that we can use to do this. On the project I was working on, this is actually 2 years ago now, this is the stack that we used. So we were using, Josh is in the other room, so he won't have to swear at me for not using Spring Boot. We were using DropWizard, very lightweight Java stack. We were using CodaHell's metrics, CodaHell, the guy behind DropWizard. I like DropWizard. The original description of it, tagline, was a bunch of libraries that don't suck much, which I think is a really nice description of things. We were using circuit breaking, so hysterex for circuit breaking. We started off using graphite, so the standard graphite stack, but in the end we moved to Grafana, purely because graphite as a UI sucks, to be honest. It's a great tool, but it does suck as a UI. And then we were using various other things in order to do Tenacity and BreakerBox, in order to do things like configuration management and so on. And then we were using CollectD at the operating system level. So that was sending us events to graphite and so on. As an example of some graphite dashboards, you've probably all seen stuff like this before. And this is an example of our circuit breaking dashboards. So in this project, which I'll describe in some detail in a bit, we had the ability to understand what each request was doing, how long it took. We had the ability to trace each request throughout the entire system. We had the ability to get that data to us, and we had the ability to visualize it. So good monitoring. I think the next thing you need, and these are the three monkeys of continuous delivery here, Dan North, Sam Newman, and Jez Humble. The next thing you need is the ability to rapidly deploy changes into production. And for that, I think there are even some prerequisites. This becomes much easier if you're in a cloud-native world where you have the ability to stand up Phoenix infrastructure in the cloud, a cloud of your choice. So continuous delivery, the ability rapidly to deliver change, So this is a standard build pipeline, as I'd sort of normally see on a project where we have a developer, tap, is able to check in some code, and that change is able to run entirely through into production, maybe with a gate at the end, but entirely through into production without manual intervention in a safe, predictable, auditable, traceable way. And along the way, we'll do some compilation and unit testing, some acceptance testing, maybe some integration testing. That's become less popular now. We'll maybe go into UAT and maybe to performance testing. But all of these things should be automated and safe. As you can sort of notice, I mean, the thing with continuous delivery pipelines is you get more production-like as you go this way, and you get faster feedback as you go this way. So this is a sort of traditional continuous delivery pipeline, with performance testing towards the end. On most projects that I start or work on now, we tend to have performance testing way up here. Because if we know earlier whether we're impacting performance, then we can do something about it. And I'll talk a bit about lightweight performance testing in a moment. So in terms of the ability to rapidly make changes, get code passing through this sort of pipeline, we then need to have mechanisms to deploy that into our production environment. And there's some fairly standard patterns now in continuous delivery, things like dark launching, canary releasing, these kind of things. And this is actually a picture of a blue-green deploy for the project. I'll come on to the example in a moment. It's Python and Botto and various things. But it actually demonstrates, what you do is you have something that's already live, you put the new version in, and then in this case we were swapping via DNS. And this represents a web app or a sort of edge-side include thing at the top and a bunch of services it uses to aggregate information from. So the ability to rapidly get changes into production. And in this case, because we were on Amazon, rapidly getting changes meant minutes, literally. And if I wanted to make a change that stood up an entirely different configuration of a particular service, we wanted 5 nodes instead of 3. We wanted 15 nodes instead of 3. That was a single line of code. changed to a single line of code, which could be pushed through our build pipeline, and suddenly we have a new cluster which we can swap over to. So we were able to make changes in hours, sorry, not even in hours, but actually in minutes. So the next thing I think we need is the ability to run lightweight performance tests. And I've mentioned a couple of tools, things like Gatling, Locust, bees with machine guns. You've obviously got the whole load runner thing. That's pretty popular in big organizations. But the things we've found very, very useful are these, right? Really simple things. Apache Bench, the server benchmarking tool. Siege, again, really simple, and Vegeta. So Vegeta is really nice. Vegeta is written in Golang, and what Vegeta gives you is the ability to fire traces through your system. Most of the others will just hammer a server at a constant rate. But with Vegeta, you can say, fire 10 requests per second for a minute, and it'll just do 10 requests per second. And you can use that as a really nice tracer for performance into your system. So I think these are the prerequisites: the ability to understand what's going on, to visualize our system, so good monitoring. I think we need the ability to rapidly deploy changes into production, so continuous delivery, and then the ability to probe our system, to actually conduct experiments. And in this case, we're using simple testing tools to do that. So the next section of this talk is about an example where we put this into practice, because theory talks are all very well, but unless you actually do this stuff, it's kind of meaningless, right? It's a nice idea. It's a nice idea in the abstract. We can use performance testing and CD to actually make changes, test whether those changes are valid ones, are good ones, and if not, back them out or carry on. But if you don't actually do this in production, if you don't actually demonstrate that this works, then I'm kind of breaking my own scientific method thing, right? In some senses, this is a recursive talk. You know, my guess is we can use this technique to make better changes to our software and better architectural decisions, right? The proof is running an experiment by doing it on a real project. So this is a recursive talk about performance testing and the scientific method. So, our heroes found ourselves up a tree. So I was on a project. It was a scientific publishing platform that was being rebuilt. It was a pretty big deal. The platform had been running for about 15 years. It had been making on average $3.5 billion in revenue a year. So, you know, it's a pretty big deal for the organization. But over time, as many platforms do, it had accrued lots of debt. It had become difficult to change. It was written in C++, and skills in C++ are, you know, they're still there, but they cost more these days, a bit like COBOL. So over time, it had accrued all this debt. And also, because it was hosted in the US, different markets that had expanded over time, so China, for example, had terrible performance. So page loads in the sort of 15-second mark. So the actual project itself was to replace this platform to do science publishing. So I'm a researcher. I write a science paper, I submit it to a journal, maybe Nature, although it wasn't Nature, and then it's, you know, gone through a peer review process, then it's made available for other researchers to read in that journal. And we were building the system that was making those articles available, and journals and books, all right? And we had these interesting requirements: improve availability, improve performance, reduce cost of delay. So get stuff done more quickly, move work through our pipeline faster. Improve performance, so we had requirements of a 1.5 second page load and a 0.8 second time to first byte. So pretty aggressive performance targets. And improve availability, because availability was tied actually to their stock price. Their stock price is tied to how many people click a button, and if the button isn't there to click, then they can't make any money. This is what we built. This is about a month into the project, I'd say. So we had sort of an edge-side templating thing which, you know, aggregated content from various other systems. We had some services going on, those blue-green things that I showed being deployed earlier. But then we had a specific computationally expensive service talking to S3. So all of our content, all these journals, all these papers were stored in S3 in XML format. Big old files, right? Megs and megs, tens of megs. And then we were using the most awesome functional programming language that's out there, XSLT, in order to transform those into HTML, which we could be stitched together in our edge side includes. But this is quite a computationally expensive thing to do. And as I say, we had these requirements of 0.8 seconds for first byte, 1.5 seconds page load. Now the nice thing is, because we were very focused on these requirements, as well as functionally delivering this project, was that we put performance tests in very early, these lightweight ones into our build. So you check in, you compile unit test. At that point, we'd fork the build, and we'd actually run like a minute worth of very lightweight performance tests. And not on representative hardware, this isn't on a production environment. But the nice thing about having it that early in the build is it can act as a ratchet. Because it doesn't actually matter what the hardware is you're running on, as long as you normalize for it. All right, so you could say, I'm running on this quite small machine, and at the moment, we're getting this one result. If I commit some code and that changes, for better or for worse, right, it doesn't matter that it's not the production machine. Over time, that comparison is still valid. Anyway, so we were running performance tests in our performance testing environment pretty early on, and this is kind of what we found initially. Ooh. It's going to give me the heebie-jeebies if I look at that. Initially, we had about 35 seconds for page load. That was the 50th percentile. So that was kind of sucky. And because we had all this monitoring in place, we thought, I'll tell you what we'll do. We can identify where the problem is, and it was in this computationally expensive service doing these XSLT transformations on XML. And we thought, I know, what we can do to fix this is this. We'll add a cache in, right? Because it's using HTTP request and response. And adding reverse proxies in front of various services is pretty straightforward. All right, so this is the idea. We take our computationally expensive service, and we put a reverse proxy in front of it to cache responses. That was the first thing we thought we'd do, whack it in there. Now, the problem with science publishing, or actually publishing in general, is that the content has a massively long tail. All right? So when a paper is published, you might get some hits that week or month, but then essentially it's completely random over time, depending on whether someone else cites it, depending on if it's mentioned somewhere else, etc. So the problem with, and obviously as we know with caching, long tails are a bit of a nightmare. All right? So I'll put these graphs together. Ideally, what we want, if we've got a cache, for a cache to work, is we want cache hits to predominate. So we want the histogram of latencies when we're hitting on cache to look something like this, right? We want most of our latencies to be down this end, low latency, but maybe the occasional cache miss up this end. The problem is with sparse caches is that doesn't happen. Right? You end up with not that many low latency requests being served by the cache, and still most of your requests having to go and do an origin fetch, which is going to take you 35 seconds. Right? So we didn't really want to straight away stick a cache in, because we could foresee these problems arising. I like this quote, and this is the famous quote, it's the original source. There are only two hard things in computer science: cache invalidation and naming things, and some bright spark added and off by 1 errors. But yeah, so let's just add a cache, right? There's lots to think about. How are we going to notify the cache when content has changed? Let's just add a cache, said no one ever. So we have this architecture. We've got this computationally expensive service. We've got these requirements. What do we do next? So we went from our initial observations of our 35-second page load, and we had to think about it. And this is the first thing. Consider performance testing, I think, early in your development cycle. I mean, personally, if I'm on a team, I like to have initial performance tests in within 2 weeks of starting a project, right? Going from nothing, no software at all, walking skeleton, performance tests, deploying to production. So consider performance early on in your development. And we actually talked about this on the ThoughtWorks Technology Radar some years ago, 2012 I think this was. We had it in Adopt, simple performance trending. This is the ability to use simple performance tests as a ratchet to know whether you're making things better or worse as you write code. The next thing is instrument and monitor, right? We have the ability to do that. This is actually one of the graphs of response time showing us our page load was pretty terrible. And we have the ability to use simple tools. We had Siege in this case. Siege, these command line tools, they're so simple. There's none of this creating user journeys that go through lots of different paths of your site. This is just hit this URL for a period of time, right? And that's often enough to get you information. And then we also had this other thing, which is, let's avoid premature optimization. And I like this quote from The Art of Unix Programming, where Eric Raymond quotes Kent Beck down the bottom. Make it run, then make it right, then make it fast. So don't design really upfront for performance. Can we use simple performance testing to iterate on what we have and get to a better place? So back to the scientific method. Right? We have our initial state. We know what nature looks like. We know what the world looks like. Right? We've got this 35-second page load. We know what the architecture looks like. So let's make a guess. So our first guess was that our XSLT transforms were really expensive, and looking at the metrics we had coming out, we could see that in the most case, they were CPU bound. So the first experiment we ran, and again, it's a single line of code, right? It's a single change in an Ansible file, was to up the number of calls on the boxes running the XSLT transforms from 1 to 8. Well, V calls, because they were virtual calls, virtual CPUs. So from 1 to 8. So that's our first guess. And of course, we deployed the changes. We ran our simple performance tests. And look what happened. We got down to 6 seconds, 50th percentile, which is a lot better than 35, but still not quite good enough, right? Still not down to our 1.5 seconds. So the second guess we made is, maybe, given our deployment architecture, maybe we could move compute to where the data lived rather than move the data to where compute was happening. So the way we had this physically deployed, it was originally we had a bunch of these clusters living in the Dublin Amazon region, AWS region, but S3 and all the content was in one of the North American regions. So essentially we were paying the cost of having to transfer 40, 80 megs across the Atlantic every single time we made a request. There was also some slightly naive coding that had gone on where actually in order to do one single transform, we'd end up issuing 6 or 7 requests for the content. So, make it work, yes we did. Make it right, remove the fact that we're making 7 of these things and only do 1, and make it fast. Can we move the compute to the same region that S3 was in? So we did that. Moving compute to the data may help. That's our next guess. And again, it's a single line of code change. Don't bring it up in this region. Tappity-tap, Ansible tappity-tap. Bring it up in this other region, right? Literally, that's all it was. We shut one set of servers down, brought another setup in a different region. Took minutes. Again, the whole change went through our pipeline in minutes. And what happened? Well, we got quite a lot quicker again. We got down to 4 seconds, 50th percentile. So we're trending in the right direction now, right? So what's our next guess? Well, the third guess, we can actually this guess was where we tweaked the transformations so that they were, again, more efficient. Actually made changes in the code, make it work, make it right, make it fast. So if we tweak these things, our hypothesis was we'd get lower page load. And the experiment, we actually used our hystrix commands as the sort of probe, because we had this nice dashboard of our circuit breakers, and we could see how long each individual transform was taking in our dashboard from the request and response. And so we could measure whether we were having an impact. And we did. We got another half a second just by, again, optimizing those XSLT transforms. So we're down to about 3.5 seconds, at which point we sort of thought, well, can we go further than this? Maybe we could actually think about putting a cache in. So finally, we did add a reverse proxy and put a cache in. And that's brought us down to about 0.2 seconds. But the problem with this is we added quite a lot of complexity into our architecture. So when we had a reverse proxy in front of our computationally expensive service, this is counterintuitive, but we actually limited our ability to make changes to that service. Because that service was offering up an API, some content, and if we wanted to make a change to that API, we had to invalidate the cache. and we're back to cache invalidation being tricky. All right. So we limited our ability to make changes to our software just by putting a cache in front of that service. And we proved this by experiment again, right? We proved this by experiment. So we got to 0.2 seconds and then realized that we had this issue where we couldn't make changes effectively. So we took the cache out again. And we put it back in below the service in front of S3. And we still got about this. And again, that's a few lines of code. Let's spin some varnish boxes up. Let's have this DNS point to it. Let's have this DNS point to it. Oh, it didn't work. Let's drop them out, bring them up somewhere else. And this is like literally a few lines of code. And we can do this in minutes. So going back to the scientific method. This ability to observe nature, understand our current state through monitoring, by which I mean instrumentation, telemetry, and visualization. Right. Making a guess, computing the implications of that guess, and then comparing the results to nature, and finally drawing a conclusion. And there is another line, essentially, that goes back up, lasers, into here, because this is a repeatable cycle. And what I think is really interesting about this technique, more than anything else, is it gets to the heart, it gets away from the sort of cognitive biases or logical fallacies we use when we're designing software. We trust our experience, or we trust that people who stand at the front of these conferences and tell you about all these cool new things, right, are correct. Right? Appeals to authority abound in our industry, right? But using this approach, you can actually prove this stuff for yourself. You don't have to take my word for it. You can go and put some simple performance tests in, make small changes, and see what happens. You can test whether different libraries are better than others, rather than take my word for it, or take others' words for it. And this allows us to take a different approach to software architecture as well, I think. Because we can go from really, really simple, make a guess about where to go next in terms of our architecture, make that guess a reality, actually run the experiment, and if it doesn't work, back it out. Right? And all the money you're spending is the time it takes you to do the experiment, which in this case was not very long. So, coming up to the end, I'll have some time for questions. So I think we should be looking to observe nature. This means instrumentation, monitoring, telemetry. We need an ability to rapidly change all the things. So not just lines of like functional code and continuously deliver that, but the continuous delivery of infrastructure as code. Our ability to stand up entire clusters or entire systems of systems of our software in the cloud. And the ability to run experiments. And we don't need to get overly complex with these experiments. Oftentimes, simple tools, Vegeta, Apache Bench, Siege, these simple tools combined with the visualization of what's going on gives us the ability to do that. I'm going to leave you, as I always do, with how the 17 rules of Unix programming apply in this case. So this is from, it was originally in The Art of Unix by Eric Raymond. These are the 17 rules. And I think these three more or less apply in this case. So the first off, rule of simplicity. Design for simplicity. Design the simplest thing you possibly can. And add complexity only when you must, and when you've proved that the complexity via experiment is necessary. The rule of economy. Programmer time is expensive. Conserve it in preference over machine time. And the rule of optimization. Prototype before polishing. Get it working before you optimize. Make it work. Make it right. Make it fast. And on that, with a little bit of time for questions, I'll say thank you very much. If there are any.
Hi, thank you for the talk. Did you measure any higher percentile for your application, say P99 or P99.9? Because you mentioned the 50th percentile, and especially when caching and requesting the same resource over and over again, this can be quite misleading. giving a misleading impression of the actual workload and user experience.
So the question was, thank you, it's a good question. Did we actually look at other percentiles other than the median, essentially? And the answer to that is yes. And I've excluded some of that for simplicity's sake. But yes. And actually, there's a really nice technique. I think Mike Nygaard talked about it some years ago at one of the GoTo conferences. He did a talk called Architecture in 5 Dimensions. And in that, he talks a lot about performance testing and how this is where those histograms come from, right? So, how if you do have that amount of data, not just on average, but all the different percentiles in buckets, you can actually, from the pictures they draw as histograms, from the pictures you can draw as histograms, the graphs you can create, you can actually see different effects happening. So you'll see a bunch of stuff at the start, which are low latency, as I've tried to demonstrate in that histogram, and a bunch of other stuff which are a result of cache misses. And they'll correspond to different percentiles, essentially. So yes, we did. I didn't include it in this. And Mike Nygaard's talk is awesome, as always. Yes. Any more? Yes.
Hey, and
Hey.
do you automate somehow those runs, or do you run them manually? Those Vegeta and Siege.
That's a good question. Do you automate? Did we automate those, or did we run them manually? And the answer to that is yes. So we had them running, they were automated as part of our build. So every single time you committed a line of code or made a change to our build, you'd get a minute performance test run using Siege. And for that minute, we then dump those results out essentially into a CSV. And most continuous delivery servers, CI servers, have the ability to randomly graph stuff. So I know TeamCity does. I think GoCD does. I'm pretty sure Bamboo does. I'm not sure about Jenkins, but you can just give it data, and it will draw you graphs. So for every build, we would have a ratchet of this is what it would, this is the performance trend. Sorry, this is the performance trend over time, kind of thing, whether it's up or down or whatever. And we could take action based on that. But we also, in the course of running these experiments, we were doing it manually too. So we were using manual probes, manual performance testing to experiment as well. Yep.
Got a question.
Sure.
Could you elaborate how you document learnings and how you keep this, learnings that you learn during experiments to reuse them and not make the same mistakes?
So, how did we document our learnings so that we don't reinvent the wheel every single time? So I would love to say, I've got a theoretical thing that I could apply to retrospectively to it and pretend that we did it. But we do use this technique on the project I'm on at the moment, and the one I was on before that, which is to use the idea of architecture decision records to capture this information. I don't know if you've come across lightweight architecture decision records, but these are a mechanism for capturing why the context in which a decision about a thing was made. Change to a design, new library that's been introduced. And again, the awesome Mike Nygaard introduced these in the blog entry, so architecture decision records. And Nat Price has written a tool which is on GitHub called ADR Tools, which from the command line allows you to create these things and put them into a known location in your code base. So what I currently do is when we have made a decision about something or found something out, then we create an ADR and stick it into GitHub alongside the code. And it's kind of nice. It sort of forms. I like the description of it being an automated team shaman. So if you've come across the idea of having a team shaman on your project, with it, this is someone who can tell you the story of how things got to be like that. So the classic example would be, a new person joins your team, they look at in the olden days, Ant build scripts, and it's awful. And they're like, how can you work with this Ant build script? And the team shaman says, gather around everyone, I'll tell you the story of the build. And this is kind of a way of automating that, right? You have the story of the decisions on your project within it. In this case, we didn't do it, but we've learned and we're doing it since. You're welcome.
Hello. Thank you for this piece. Have you ever experienced the failure of this method? So, for example, you have drawn the conclusion that the change was successive, but it wasn't. And it was realized after several times, because actually you did the test just after the application started with this change.
So the question is, were we looking at the wrong data? So for example, I'm a bit of a performance testing geek. So for example, we didn't wait for things to warm up, say JVMs, or we didn't wait for caches to warm and that kind of stuff. Is that the question? So we could have experienced wrong data.
After a day or a week, you realized that the change actually wasn't successive, but the first impression was that the change is okay.
Right, okay, so over time, did we see that this led to us having to back things out? We didn't. I could see how that could be possible, and I think what you would do is run another experiment to prove it, and then back it out. So yeah, I didn't, we didn't, but I can see how that would happen, and that's fine, right? Because failure is also a thing. Failure is also success. Because you've learned something, right? Any more?
How do you choose the cases for your performance tests? How do you decide whether this query is better than the other one?
Good question. So how do you, what guesses do you make?
Yeah.
Right? So you start off with a view of the world, right? So you know how your thing is performing at the time. And based on, I guess, experience, you make the best guess you can.
Okay, but this automated suite which you're running with every build, it contains a few cases, or just to test the regression, or how it's organized?
Yeah, so the automated part of it is literally just to test performance regression. The rest of it is to do the experimentation. Yeah.
Okay.
And it's it's like anything in science, right? You can. It doesn't matter who you are. You don't have to have a PhD in order to make a really good guess about how the world works, and actually make a major breakthrough. Yeah, you can win a Nobel Prize without being a doctor. It's just about the accuracy of the guess and whether it agrees with the real world.
Okay, what do you think about the replication of traffic from production into some kind of test environment as a sort of the continuous performance testing?
So can you do Yes. Well, so this is one of these things where I think you'd have to think quite carefully about doing it, because these sorts of things have a habit of starting off as a really good idea, and then 6 months down the line, when everyone's forgotten about why we were doing it, something really bad happens with production traffic. So we've added a new field into our production, into a microservice which has got personally identifiable information in it, say. And we forgot that we're piping this stuff through into our test environment, and suddenly we've got personally identifiable information flowing through our system when we shouldn't, and we're breaking the law, say, right? Same with correlation IDs. There's a famous example of, if you add correlation, or if you add synthetic transactions. So I'll run a test transaction through production, once every minute or something as a probe to make sure we're working. That's fine it's fine up until the point where you forget, or someone forgets there's a test transaction, and you start treating it as real data. And I think that happened at, I can't remember which organization it was, but it happened, and they ended up reporting extra revenue based on their smoke tests rather than the actual real data. So yes, but be really careful, I would argue.
I think that's quite safe for read-only services. Yeah, or maybe it is more safe for read-only services, but I think that it's a very nice way to learn about cases which you couldn't come up on your own, to get this inspiration for production.
Yes, I agree with that comment. I would sort of consider that to be like a continuous soak test. And there are other ways of doing that. So you can actually just get a dump of a day's worth of data. And actually, you can do things like play with time, so compress it, expand it, do all sorts of cool stuff, but essentially send a representative workload through, rather than just how fast is this going, maximum leap or something. So I think that's my time up. So thank you all very much. Thanks for the questions. I'll be around the rest of the day. See you all later.